Let's show maybe it's a how-to. This presentation is a how-to and how to launch jobs to the queues, to the cluster, and maybe some advices in how your obtain the times, the memory requirements, the course. Okay. So let's start. You are here because you have a problem. You have a computational problem that, fortunately, you know how to solve. No, you maybe need the geometry of a molecule. You need the harmonic of a structure. You need to solve the orbitals of a molecule using Hartree-Fock, DFT, using molecular dynamics, and so. But when you try to solve in your own computer or your own workstation, you have a problem. In fact, you have three kinds of problems. Maybe that it spends too much time. Maybe you need too much time and it's impossible to solve in human time. Maybe your problem is too big and it cannot be allocated in memory. That's typical too. Or your data needs too much storage. For example, if you need to align a genome or so, and your hard drives cannot allocate that amount of data. Okay, what's the solution for this? Our typical solution, the engineer solution is, okay, if I need to figure something, I provide more cores, more memory, and more faster storage. Okay, that's we have in a cluster, more of everything. Okay, so how we manage this? Ismael showed you the scheduler, but the scheduler only manages the resources that you ask. But how many resources have you asked? Okay, that's our problem. First of all, you need to know what is your lack. You are not enough compute power. You are not enough memory, or you are not enough I/O. Performance in your disk or quantity. Okay, so first of all, you have to answer this question. Okay, in order to now to get an answer without using a profiler or a professional or IT tools, you can do three things. The typical things that you can do is, first of all, is if you use more cores and you get less time, it's compute bound. Okay, so you can solve your problem using more cores. Otherwise, if you're using more nodes or better memory, you get more performance using the same amount of cores. Is memory bound in general. For example, DFT, Hartree-Fock. And if you have a lot of data and you get results faster using better hard disk or more nodes, it's I/O bounded. Okay, so that's why you use a cluster, because you can solve this kind of bottlenecks in a one solution. Okay, for this we have three strategies as known as MPI. When you use multiple instances of your program working separately in different nodes in order to get the full performance of all nodes, that is a more versatile and more flexible. Okay. Other strategy is OpenMP, or the threaded parallelism, that's known as. Okay, for example, Gaussian, it's a typical Clustal for an element. It's a typical OpenMP strategy. These kind of strategies has a problem that cannot be used in some nodes, only in one node. So it's limited by the amount of cores that you have in a node. Okay, and the newest in some way strategy is the accelerated systems. For example, the GPUs. This strategy is kind of OpenMP, but in a higher order of magnitude that use the computational power of a GPU that it's higher than a usual CPU to produce mathematical results. Okay, so in other place, in another way, you can use some libraries. Okay, because you don't need to know how to program or how to use the previous strategies, OpenMP, MPI, or QDAP, for example. Someone coded for you. For example, if we have the mathematical libraries, LAPACK and Intel MKL, math kernel libraries, we have Fourier transforms, for example, fastest Fourier transform in the West, or the CUDA fastest Fourier transform. Or if you need manage a huge amount of data or parallelize your I/O, use HDF, okay, theoretical data format. Okay. In summary, first of all, you have to know what do you need to parallelize, okay? In general, is the solving algorithm. Then, how much resources do you need? How many resources? Okay, more memory, disk, and CPU. And then select your parallelization strategy. In general, this strategy is selected by the coders, not by you. In general, for example, if you use VASP, you can use everything of them because both MPI, OpenMP, and CUDA are implemented. But for example, if you use Gaussian, only you need in a first approximation OpenMP, and in some few cases CUDA. And if you use Linda, you can run in parallel. But for most of Conda, for example, Conda implementation from something, typically is OpenMP threaded. Okay. So now I will teach you how to write some Slurm code, for example, to launch the cluster. First of all, you have to identify the parallelisms. Okay. The threaded parallelisms, if you make a top in your job, for example, if you are in your computer, you have a test of your problem before launching to the cluster, and you are not sure that if it's a threaded, a process, or a GPU parallel, you can use the top command to have a clue. Okay, in general, the threaded parallelism has a performance in the percent of GPU more than 100%, and only in one task, as you've seen in the Gaussian, in the L904X. On the other hand, if you have a process parallelism, that is MPI, you have a lot of instances of the same executable. For example, that's a star CCM executable that is running in 8 instances, each one in 100%. Okay, that's at a glance and one way to recognize if you are in a threaded parallelism or process parallelism. Okay, so after that, you have to allocate or assign the amount of memory that you need. How? Okay, you can get it from top again. Okay, top say you how many resources or how much amount of something are you spending in each job. For example, Gaussian is spending 47 gigabytes of memory. Okay, so you have to ask Slurm the amount equal or upper of 47. On the other hand, the MPI parallelization creates a lot of instances, but each one needs its own amount of memory. So if you see, you 1.3 gigabytes, 1.3 gigabytes, 1.3 gigabytes. So you can access Slurm the amount of memory per CPU, 1.9, 1,900 megabytes, or you can ask for the total amount of memory. For example, in the case of Gaussian, 64 gigabytes. Okay, Here we have the amount of default of memory of each queue. The standard around 2 gigabytes, the GPU around 6 gigabytes, and the FAT partition around 16 gigabytes. Okay. So now, how many time? How much time? How many hours? How many days? A first approximation is if you have a previous test on your computers, the typical solution is make a linear extrapolation. If in your computer with 4 cores takes 1 hour, in a supercomputer with 2 cores, it should take half an hour. It's a more basic approximation. Obviously, it's not exactly because your computer and an HPC node don't have the same characteristics, but it's a upper limit to the time. Okay, because the time cannot be at first sight if you are don't make a test, it's impossible to guess. So, as I said, first of all, you have to identify the paradigms, if it's serial, if it's threaded, if it's MPI or accelerated by, for example, a GPU. You have to estimate the amount of resources, how many cores, how much memory, how many GPUs, and try to estimate as better as possible the runtime. Because as more runtime and more cores and more memory you request, probably more time you will be in the queue waiting for your resources. Okay, that's a clue. As Ismael said, try to be optimal in moving your data, because you are spending time moving data maybe that you don't need. Okay. So one example, for example, Gaussian, it's an OpenMP application. For the first line, it's saying what's the name of your job, Gauss16 test. The output file, Gauss test, the %J, it's the job ID. It's a shortcut for the job ID. Okay. The error file, you will need one task because it's threaded parallel, and you will ask for 16 cores, one for each thread. You will send you to the standard partition, and you will need the total amount of 15 gigabytes. And your runtime will be 10 days for maximum. Maybe it will be take less. Now you ask the system that you will going to use Gaussian to set up the environment with module load Gaussian G16V1. And that's, from this moment, that's your real job. You set the input dir, home, Gaussian test inputs, your output dir, home, Gaussian test outputs. You change your directory to scratch. Where is your job ID? I later will see how. You'll copy your inputs and you launch on Gaussian. After finish Gaussian command, you create the output dir and you move your data. Okay, that's a typical OpenMP job in Gaussian. That it should this script is functional, so you could copy, launch it if you have the input. Your input is called input. It will work. That's a VASP example. Same structure. Okay, the job name, the output file, the error file. Now you need 24 tasks because VASP in this case it's MPI, so you need 24 instances of VASP using one core each one, and you ask for the memory for each one of these tasks, 1.5 gigabytes. Okay. And you will need 20 minutes. You load the module of VASP 544, and the same as Gaussian, you define your inputs and you launch your job with srun. Why srun? Because srun, it's a wrapper for MPI run, that is the way for launch MPI jobs. SRAM will get the information of the nodes and the cores allocated for you from SLAM. So you will not to provide it. Okay, it's automatic. And that's it. You will wait for 20 minutes for finish your VASP job and you get the results. Okay. Another more difficult example, GROMACS. GROMACS is a molecular dynamics solver that it's hybrid. Hybrid seems that you can use OpenMP, MPI, and accelerated solvers at the same time. So you need to say to SLAM that you are using a hybrid configuration. How? The number of tasks, in this case 32 tasks. Each task will take 2 cores to the OpenMP part, and then you will ask for 2 GPUs with GRES GPU 2. You will saying that you need 2 GPUs by node. In this case, you need only 2 GPUs because you are only in one node with the capital N. Okay. The second part is the same as usual. The module load your GROMACS and the SRAM command with your GROMACS executable and your GROMACS options. Okay. And then let's. I don't know if you have some questions until now, and now I'm going to share my terminal and show you how launch in real some. Okay, so let's. I'm going to stop sharing. Creo que puedo compartir. This and this. Okay. Can you see my terminal? No? Okay. So first of all, I have to join the computer. Vale. So I'm going to. Okay. First of all, I'm going to log in the computer, the cluster. That's all I have. Okay, the login message with some info, the status of the occupation. Okay, and now going to my data. Okay, data is set up for every user and it's your own path. Okay, in my case it's data CSU como yo. In your case will be data, your group, and your username. Okay, I'm going to my folder when I have 2 examples, NumDy and VASP. Okay, I'm going to start with VASP. Okay. I'm going to launch. Okay, if you see, I'm going to show you my Slurm script.
Hay un problema con no están viendo la pantalla bien, no sé exactamente.
¿Qué veis?
No sé, yo lo veo bien.
¿Y alguien no lo ve?
Sí. Solo una parte.
Oh. Maybe it's only a problem with your Teams client. Yes, I can. Okay. No. Okay, I'm going to show you the script. That's are my SLAM directives, the job name, VASP test, the output file, error file. I will ask for 8 tasks, 8 cores in one node, and the express partition because it's a small test. Okay, and I need a quick answer. Okay, I load my VASP module 643. I say in my work dir will be slurm submit dir. That it's the slurm submit dir is the place when I make I execute the swatch command. Okay, and I will copy the 820 molecule to my Scratch directory that is defined by Slurm at the moment I launch the job. Okay, and that's my srun command, which wasp. Let's go. So let's see. Okay, it's going to AMD AMD 01. So I'm going to do a top to show you how you see the execution. If you can then change the user by only show my user, and that's only my. And I start Scratch. Wasp test. Wait, let's submit a batch job to the number, and I can see my queue, SQ with SQ. If I do this, I see the queue of everyone. It's not that I want. I prefer to see my queue, and that's what I have. It's running in an AMD 01 with 8 GPUs. It's taking 21 seconds for the moment, and it's running in the Partition Express. As I said, I see some VASP instances using 100 of CPU each one, as expected, and it taking 0.1% of memory. So around less than 2 gigabytes. It takes some. If I want to see my job running, I go to Scratch, and it's finished. So, but I can say it. I go to the job ID, and here are my results. Okay, that's my Scratch files, or all the files created by VASP. Okay, I go again to data. And see the results. The error and output file is created by Slurm. You can see that it should be the data showed by the terminal if it were an interactive job. Okay, so in this case, here are in a file. Okay, the output, the out card generated by VASP. And that's it. It should be the usual workflow of the flow of a job. Okay. Now, NumD. I will use NumD. I start with NumD because it's a CUDA application to see you how to launch in a GPU. In this case, it's quite different because VASP was a simple execution. Now I do some kind of scalability test. As I say if you are not sure how much time or how many GPUs do you need or how many cores, because it's the first time that you launch, you can perform a scalability test. That is, in other words, try some different configuration of cores, memory, or GPUs in order to get the fastest. Okay, so it's how to look like the kind of scalability test. Okay. I'm going to launch this command, an NumD3 with some CPUs and 2 GPUs, okay? 2 devices, 0 and 1, because we have 2 GPUs by node. With 8, 16, 32, and 64 cores, and get or choose which will get the best performance, okay? So I'm going to delete the previous outputs. That's it. And I'm going to launch. In the queue, I'm going to check where is executing, in which node. In GPU 2. So I'm going to GPU 2. Zero. And top. NumD in this case is an OpenMP, so it's threaded. So you will see in this case 32 cores, goes 3,155% of GPU, That's a command NumD. And if I want to check what is the performance of my GPUs, I use this command, NVIDIA SMI. And I have two instances of NumD, one of each GPU, and now are performing at 6 and 5%. So in this case, because it's much more problem, it's the example of NumD, the Alanin example. I only using the 6% of each GPU. So I will, if I were strictly, or I would optimize my performance and my runtime at the use of resources, I will use, in this case, one GPU. But it's an example, okay? We are using one GPU that is spending 6% of each one, okay? In two GPUs, sorry. Again, now it's running with 6 CPUs in effective. Now it fired me, so it finished. I'm going to check my queue. Okay, it's empty, so it finished. My result for 16, for 32, and 64, and 8 cores. I'm going to make a tail command, okay, and NumD out everything to check the time, the run times. Okay, with 16 cores, 30 seconds, 32 cores, 11 seconds, 64 cores, 68 seconds. Curiously, it's counterintuitive, and 8 cores, 13 seconds. So in this case, the best performance is around 22 cores. That's a scalability test. And that's it. I don't know if you, well, you can see the results in ACCT. That's my last jobs. For example, the last one was this, the BASP job completed. The difference between the BASP job and the NumD jobs is that in NumD, if you see, I use NumD test SLM. I used 1, 2, 3, 4 times the srun command. For Slum, that's our job steps. And you see 1, 2, 3, and 4 instances of the job. In another way, only one use one instance of BASP in this run, so I only have one. Okay, I don't know if you have some questions. No, there are no more questions. So, yeah, obviously that's an example. It depends on it depends on you. Sometimes some applications, for example, BASP, if only you need one task or one core to each GPU. For example, NumD can get better performance if you also use the CPUs in your computing node. It depends on the application. Obviously, if you only can't use the GPUs, again, obviously it's a waste of cores. Why you need 64 cores if I only need the GPU? But in some cases, for example, GROMACS also use also the CPUs to do the job, not only the GPUs. But for example, in other programs, you only need the GPU. For if you need 4 or 12 cores to the whole node, it will be enough. When you try to allocate more than 80 of GPU, well, you can do two things. You can use more nodes, more computer nodes. If your, because the memory per CPU it's constrained by the total amount of the node. If your node have 100 gigabytes and you have 10 cores, the memory per core is 10. It's the ratio. If you need more memory per CPU, or for the GPU, you will use more nodes to get the desired ratio. That's the only way. If you cannot reduce your requirements of memory, you will get more resources from the cluster to set it. It depends. In some cases, yes. In some cases, no. For example, GROMACS escalates really, really well. NAMD also too. BAS, in some cases, in some systems, in some solvers, it depends on the application, the solver, and the problem. There is no an answer. You have to test it and decide if you'll get if your problem will degrade or not. There is no an answer. I think no one is writing. I think so.
So if there are no more questions, we will do a short break now, and we will be back at 12:15.